Hello everyone, and welcome to the fourth lecture of Shaastra Spotlight on the MTX Day 3 of Shaastra 2021. Adding to a bigger and better lineup this year, we are extremely honored to have with us today Dr. Barish for a lecture on understanding our universe with gravitational waves. Dr. Barish is the Linde Professor of Physics Emeritus at Caltech and Distinguished Professor of Physics at UC Riverside. He's one of the founders of the Laser Interferometer Gravitational-Waves Observatory, LIGO, which discovered gravitational waves from the collision of two black holes. Dr. Barish also led the design of the International Linear Collider, a global collaboration that will pursue the understanding of Higgs Boson. Dr. Barish shared the 2017 Nobel Prize in Physics for his decisive contributions to the LIGO detector and observation of gravitational waves. Thank you so much for joining with us, sir.
Thank you.
Further ado, let's begin with a fascinating lecture on understanding our universe with gravitational waves. Over to you, sir.
Okay, thank you. Let me share the screen and then I'll start.
Sure.
Can you see my screen? Okay, is my screen visible?
Yes, sir. Yes.
Okay. Thank you for inviting me, and I'm very happy to be able to talk to you today about gravitational waves. My objective today is to show you what gravitational waves are, why were so difficult to detect, and what promise they give for science in the future. So it's going to cover a lot of territory, but I'll try to make it understandable to all of you. So first, the whole story, or the beginning story, is in the picture I have on the lead slide. If you look at the picture to the left, on this slide, it's the discovery figure that was basically on the front pages of newspapers around the world when we saw gravitational waves, and was the figure number 1 in our paper that described gravitational waves. So if, when we're finished with the first part of this lecture, you understand this figure, you at least understand what gravitational waves are. Let me just say what the figure is. We have 2 different scientific instruments to detect gravitational waves. The first one is in the state of Washington. I'll show you that. And the second one in the state of Louisiana, both in the US. And the figure that's shown here on the left is the data from Hanford, Washington in the top frame. And on the right is the data from Livingston, Louisiana in the top frame. And they look very much alike. You should see that. What they are is what we call a chirp signal. It's what happens in gravitational waves when some objects merge and give gravitational waves. They first give a lower frequency, meaning these are wider, and then they get narrower and narrower and come together when the objects merge. These 2 objects are what we call black holes. How we know all that is by looking at the next diagrams down here. And if you look at those, that's the calculations of what we say we've just seen by using Einstein's theory of general relativity. And it's clear by eye, this is raw data. We've done nothing to analyze this data and change it. It's just what comes out. And you can see that it looks very much like the data below it, except of course it's experimental data, so it's got extra wiggles and so forth because of our accuracy. The scale is 0.2 of a second this way, so time goes to the right, and the size of the signal is the vertical. But the size of the signal is tremendously small. I'll show you that in a few minutes. But that number is 10 to the minus 21. That's 21 zeros and a 1. And that I'll describe to you. If you take, and what convinced me right away that we saw what we saw, is that if you take the data and you take Einstein's calculations and subtract one from the other, you just get a bunch of wiggles, which is the experimental errors, and nothing indicating that there's some difference in shape between the Einstein equations and what we observed. and we did it twice. So that's the data. I'll show you that in a little bit more form as we go along. But let's start by going back. We all learned gravity, whether we're science students or not, when we were kids, and we learned it from our teachers, and it was based on Newton's theory of gravity. This is the most famous and successful physics theory ever. It was written in 1687 by Sir Isaac Newton. It was written in a book called The Principia. That book is a famous book that you'll find in libraries. There's just, I think, less than 100 copies in the world. And so very good libraries will have a copy of the original book called The Principia. And in that book, Einstein did two things. He wrote down what we call the scientific method, the way science is followed and done to find the truth in anything that's scientific. And he wrote down his theory of gravity. That theory of gravity, for our purpose today, he wrote it in a whole book, but for our purpose today, I'll remind you what it is. That is, if we have two massive objects, something that weighs mass, it could be big objects like the moon or the earth, or it could be just two balls that have mass. There's a force of attraction between them. That's gravity. Gravity pulls them together. And that force is proportional to the product of the two masses divided by the square of how far apart they are. Inversely proportional to the square of how far apart they are. And the force on one is equal to the force on the other, and they are pulling toward each other. The actual calculated size of the force is in this constant here called G. And that constant took 100 years after Newton's time to determine, but it was determined using a device in Britain about 100 years later. So this theory of Newton's was fantastically successful. He gave it a name. He called it universal gravity. What he meant by that is that it works for gravity no matter where gravity occurs. There's not a formula that's to be used for the moon going around the earth and something else for some other phenomenon like the apple falling out of the tree that requires gravity. It's universal. And it's the formula that I said here. More than 200 years later, and I'll talk about why we have a new theory, and it took more than 200 years, Einstein wrote down a new theory of gravity. I write down the key equation here, but I'm not going to explain it. I'm just doing it out of completeness. Einstein's theory of gravity is very difficult mathematically, and I'm just going to hint at it tonight for this lecture. But that theory is based on space and time. We all know that space is three-dimensional and time is one dimension. And he unified space and time. It becomes one word, space-time. And that is what Einstein's theory is about. And I'll show you what the effect is to create gravity and why we now use Einstein's theory of gravity instead of Newton's theory for most things that have any sophistication. There was nothing wrong with Newton's theory of gravity. It's the way physics is done. So it's not that Einstein's theory showed that Newton's theory was wrong. It's that as we develop our understanding of physical principles, we understand a more sophisticated theory that can explain things that an earlier theory might not have been able to explain. In this case, I'll illustrate this. So Newton's theory worked completely for more than 200 years, the most successful theory ever. But it had some insufficiencies. First, by the time Einstein came along, there were no measurements of anything that disagreed with Einstein's theory, with Newton's theory, except one small difference, which perhaps could be explained away. That difference was the orbit of the planet Mercury around the sun. As Mercury goes around the sun, it comes back. It's then pulled by the presence of all the planets and moons and so forth in our solar system, and it comes back to a slightly different place. And then it does it again, kind of a daisy pattern, like daisy leaves. The distance, or the amount that it moves going around one time, can be calculated using Newton's theory. And if you use Newton's theory and calculate it, it's almost right, but not quite. So the answer from Newton's theory is that it'll move forward 532 arc seconds in a century. And the observed amount is about 10% larger than that. So as impressive as Newton's theory is, the only difference that was seen was a rather small one, a 10% difference in Mercury, in the planet, in the orbit of Mercury around the sun. And in fact, that could be explained, and a lot of people try to, if there were some undiscovered objects or object, another planet, say, or some continuous objects between Mercury and the sun. So a lot of searches went on in the 19th century looking for objects between Mercury and the sun. There were false discoveries, but by the time Einstein came, that was an unanswered question. It was searched for later by NASA in a very sophisticated set of space experiments, and nothing was found between Mercury and the sun. Einstein's theory, which I'll not describe in detail, got the right answer for this. So the first reason to take Einstein's theory of gravity after 250 years seriously is that it got the right answer for Mercury going around the sun, while Newton's theory was wrong by 10%. There were more conceptual issues which were a problem with Newton's theory. So we knew it wasn't the ultimate theory of physics. The first one is, and Newton recognized this one, Newton's theory, when he wrote it down, he recognized that it had a problem. And the problem is that if the apple falls out of the tree and you watch it fall out of the tree, it's okay. You see it happen when it happens. But if the distances get long, Newton's theory has nothing that makes it take some time for the message of what's happening to travel, say, from the apple to you. So an example of where there's a problem is, imagine our sun. Our sun is burning all the time. Just imagine that it disappeared right now. If it disappeared, we know that it would take 8 minutes before we would know about it, because that's how long it takes light to come from the sun to us. It's inconceivable that we would know about the gravity immediately. It has to take some time too. So the finite speed of information travel is missing from Newton's theory. Newton recognized that, but it didn't fit into his theory, and it didn't matter for most things that he cared about. But this is an illustration of where it would matter. Einstein's theory, in Einstein's theory, gravity, the signal, the message from gravity, goes at the same speed as the speed of light. So in that case, if the sun disappeared now, we would learn about it both from whatever happens gravitationally that it's disappeared, and in terms of the electromagnetic or the light signal 8 minutes after it happened, both. So that's the first problem of Newton's theory that would be solved, other than the right answer for Mercury around the sun. There's a second one, and it's more dramatic, and that is Einstein did what you should do in a new theory, and that is, if you have a new theory of physics, then it should fix what has to be fixed, but it just fixing a problem that existed in an old theory isn't the whole story. It should predict something that we can measure that's new. And in the case of Einstein's theory of general relativity, that turns out to be true. In his case, the problem is that the way gravity works is a distortion of space and time. So that what happens, and I'll show you why in a second, if light were to travel close to a massive object, it would bend by Einstein's theory. And that could be tested. And Einstein proposed that it be tested by looking at a full eclipse of the sun and watching the apparent position of stars that are behind the sun as they go behind the eclipsed picture of the sun. That was seen, and not only was it seen that there was a curvature of the light, as Einstein had said, but the amount was precisely the amount that Einstein had calculated. So that you can see in the picture here, the same idea, the bending of light going around the sun. But look on the picture on the left. On the right, I'm showing the eclipse of the sun, and you see as the stars behind it, it curve around the sun. But if you look at the picture on the left, you'll see that that's a picture of the sun and the earth. And below it is a grid of the space. If you didn't have Einstein's theory, it would just be a flat grid. But if an object that's massive distorts space, it changes that grid to look like a big distortion near the sun, a smaller distortion, which you can also see from the Earth. And it is this distortion that determines what gravity is doing. It's the fact that you've created a well here that makes the Earth want to fall in toward the sun. And it's only because it's going at high velocity around that there's also a force called centripetal force that keeps it at the position it is away from the sun. But if we talk about the apple in the tree, this distortion of the Earth, of the space around it, is now what causes the apple to fall to the Earth. And that basically explains why the apple falls to the Earth. Newton didn't explain that. Your teacher, when you were young, told you that if you jump up, the Earth pulls you down. But did you ask the teacher why it pulls you down? Newton never explained why. Einstein's theory, with the distortion of space and time, explains why. It's basically this distortion that creates a well that makes you fall down toward the well. So this was a very famous discovery that Einstein predicted, that you would see the distortion of the light beam from a star going around the sun. And this is on my right, the headlines that were in the New York Times after this was observed, which were strange. The idea that light would bend was such a crazy idea that even the New York Times made fun of it, saying light's all askew in the heavens, and about the men of science basically seeing crazy things. So it didn't make a lot of sense, but it's been proven over and over again. Often in physics, something that's a new discovery, like the fact that light bends, then becomes a tool for us. And in astronomy, the fact that light bends has made it a wonderful tool. It's what's called gravitational lensing. So we can look at an object now that's dark and study it by the fact that light, when it goes around it, bends, and we can learn something about this object, how big it is, what its mass is, how much it bent the light, and so forth. And so we do in astronomy something called gravitational lensing, which is no more than taking advantage of the fact that light will bend when it goes around or goes past a massive object. Okay, with all that in mind, I want to go on now to the final prediction of Einstein. So the first thing he did was make sure that he fixed the only problem that existed in Newton's theory. Then he explained why the apple falls out of the tree, and he explained something new, that light would bend, and he explained that it takes finite time for you to know that something gravitational happened, the example of the sun. Lastly, he made one more prediction, and that is a year after he introduced this theory in 1915, he predicted in this little German article that I wrote here that there would be waves in gravity, what we call now gravitational waves. This was in analogy to the waves we have in electromagnetism. So in electromagnetism, we have a set of waves. Einstein recognized, again, being Einstein, that the equations that he had developed for general relativity to explain gravity had certain similarities to the equations of electricity and magnetism. Being Einstein, he then made the extrapolation that if electromagnetic waves, if electricity and magnetism has waves called electromagnetic waves, and the equations look so much like the equations of general relativity, then gravity, which is explained by general relativity, must also have waves. So he predicted in 1916 that there would be gravitational waves. We detected those 100 years later. The first publication was just a small publication in 1916. It actually had some errors in it, but it basically predicted the existence of gravitational waves. He wrote a second paper two years later in 1918. He fixed the little errors that were in the first one. But he also told us how gravitational waves are formed. And if you recall, in electricity, how do we form electromagnetic waves, radio waves, whatever? They come whenever we have two charges. If you look at my fingers, if we have two charges and they oscillate between them like this. If you have charges that oscillate, they create waves, and those waves can be detected. That was the famous experiment of Hertz done in about 1880 something, that he made a little source that did this, and then he moved to the next room and detected that there were signals, electromagnetic waves, and he moved toward the source and away from the source and saw that they were like waves. They went up and down. The same thing then should happen for gravitational waves, according to Einstein, only the source isn't some two-charge system that's wiggling, but a four-part system, something we call a quadrupole. So something that has a quadrupole moment. An example of that is two objects going around each other, like the Earth around the sun or the moon around the Earth. Or in our case, it's going to be two black holes going around each other that we detected. So gravitational waves, I've drawn a picture here of, for example, two black holes going around each other, or it could be the Earth around the sun, only these are pretty much the same. As they go around each other, they radiate away gravitational waves. That's radiating away some energy. As they radiate away some energy, they slowly in-spiral toward each other and eventually merge together. What we've detected in the signals I showed at the very beginning was this final merger when they come together. And so that happens. And the waves that go out, as I indicated before, will travel at the speed of light in Einstein's equations. Okay, this was very controversial. A lot of people didn't believe it. It wasn't derived from first principles. Einstein instead had inferred it by the fact that the equations looked a lot like electromagnetism, not because he could derive them from first principles. He returned to the problem to try to derive them 20 years later in 1936. I'm trying to illustrate kind of how an idea comes and how long it takes to believe it and how long it takes to test it. So 20 years later, Einstein returned to the problem, trying to see if he could now calculate that gravitational waves exist coming out of the formulas of general relativity. When he did that, he got himself in trouble, and he got in what we call what are called singularities or infinities in the calculation. That made him worry that basically he was fooling himself, that gravitational waves maybe don't exist because they're an artifact of some problems in the solutions to the equations and they aren't real. He submitted then a paper to Physical Review, the main place where we publish papers, Physical Review letters, with an interesting title. It is, Do Gravitational Waves Exist? A very funny question for him to ask 20 years after he proposed they exist. So he's now questioning whether they exist. That article was then sent to referees, the way we do it in what we call peer review, in creating an idea or an experiment, and then other professionals review it. The reviewer saw where he had made a mistake, and but Einstein never quite reconciled this himself. And so it was still an open question when Einstein died in the early 1950s. So he proposed gravitational waves in 1916, and as late as early 1950s, we still weren't sure. Theorists weren't sure because of these calculable singularities that gave infinities. Einstein wasn't sure, and they weren't sure. Then there was a conference. That conference is when now physicists believe that it was the point at which theoretical physicists started to believe that gravitational waves had to exist. That was a conference held in Chapel Hill, North Carolina. It had about 40 of the leading general relativists in the world at the meeting. And at that meeting, basically the question of the meeting itself was the gravitational wave problem, is what they said. Do they exist or don't they exist? And at that meeting, there were two presentations that convinced the theoretical physicists of the world, the ones that mattered, that gravitational waves had to exist. One was a talk by a theoretical physicist named Pirani, and he derived, like he would do in electromagnetism, from the equations of general relativity, he derived the equations of the waves that would come out, called gravitational waves, from something that Einstein had tried to calculate but had difficulty calculating. But Pirani did it beautifully and demonstrated it to the audience. The second thing that happened at that meeting is that Richard Feynman was at the meeting, and he then made a talk where he said that if gravitational wave, that's a picture of Feynman, if gravitational waves exist, it's not just a mathematical problem, they have to be able to do something physical. Otherwise, we're talking about just something mathematical. And so what he said is if gravitational waves exist, they should be able to transfer energy. It's an energy that's emitted from the picture that I drew of whether it's electromagnetic or it's gravitational. You should be able to see that transfer of energy somehow. And he made up a way that could be done in his head, what we call a Gedanken experiment. So imagine that you had a rod, and the rod itself, shown here, had a couple rings on it, and then a gravitational wave goes through. The gravitational wave will cause the rod to expand and contract as the gravitational waves go through it. When it expands, it puts tension on the rings, moves them, and heats them up actually because it creates some friction. That means that what's happening in this Gedanken experiment is that energy is being transferred as heat from the rod to the rings. And that's a transfer of energy, and that's demonstrated that would happen from the phenomenon of gravitational waves. So at that point, it became an experimental problem, not a theoretical problem. gravitational waves certainly existed. Theoretically, they could be calculated from the basic equations of general relativity. They could do something physical that made you feel that they were a real phenomenon and not just a mathematical phenomenon. So the problem came to detecting them experimentally. It turns out that it's a difficult problem. It's a difficult problem just because of the way nature is where we live, and that I'll try to explain to you. Basically, first, the waves themselves are not like electromagnetic waves. They don't have the equivalent of a photon or a graviton with them in the classical theory of general relativity. So they're basically ripples in space and time itself. They pass through space and time, and they have an amplitude for the sources that I'll talk about of 10 to the minus 21. That's a tiny, tiny, tiny number. That's what I said earlier. And so it means this little h, which is what comes out of general relativity, the little h, is 10 to the minus 21. It means that a change of length, because of the distortion of space-time, is only 1 part in 10 to the 21 of the size of whatever I'm measuring. And so if I imagine a ring of free masses, they're just sitting here, and then a gravitational wave goes right through them, what will happen? What will happen is it distorts it so that it becomes elliptical, and the distance, the little distance delta L, is 1 part in 10 to the 21 of the diameter or the radius of the ring. So that is how much it will change. It's tiny. It has a frequency. Gravitational wave might be happening 10 times a second. So it'll look like this, and the next it'll go to being distorted horizontal. It'll go back and forth between vertical and horizontal. Since the effect is so small, 10 to the minus 21 is a tiny, tiny number. That is why when you see the picture of the apparatuses that we use, we made it not a meter in size, like I've done in this picture, but kilometers in size. And that means the effect is more like 10 to the minus 18 meters, still a challengingly small number that we would expect to see in an apparatus that's kilometers in size. This is the first attempt to do gravitational waves, and it's effectively Feynman's experiment. It's a big bar of aluminum. The person here is Joseph Weber, first experimentalist to look for gravitational waves. And he put piezoelectric crystals around it with the idea that this big bar, if a gravitational wave comes through, would distort, make some pressure on the piezoelectric crystals, and he'd pick up a signal. He actually made, this was in the 1960s, so a decade after the theorists agreed there were gravitational waves. He claimed that he saw gravitational waves. Unfortunately, he was wrong. It was just background in his experiment, but he was the first one to actually try to look for gravitational waves. Now comes the actual detection of gravitational waves. There's many sources, as you can imagine, that we can imagine that will give gravitational waves. But one of the most attractive ones, or something that we know happens in the universe, there are a lot of binary systems. That is, systems just like there are, like the Earth and the Sun, or the Moon and the Earth, that you have an object, there's another object going around it. So there are many binary systems in astronomy. And so if we look at binary systems, they will make gravitational waves. I show that in the figure on the left. If I have the in-spiral of two compact objects, they could be black holes, they could be neutron stars. But when they go around each other, they are spinning. It makes the picture I have on the left here, which is what we saw in the detector. Then eventually they merge together. As they merge together, they make some signal that we can't calculate. And then eventually all the quantum numbers and everything have to make sense. And they calm down. So they come down in what we call a ring down. This is just examples of what it might look like if they're heavy, what it would look like if they were lighter particles, where we'd see more oscillations. So that's what we're going to look for, and we build an apparatus to do that. The apparatus itself used a principle that we call interferometry. And the idea here is that if space gets distorted in the way that I'm showing in this picture on the left, then the distance up compared to the distance sideways at any given time changes. And that means that if I manage to try to measure this distance and that distance at any given time and monitor it over time, we'll see changes. And that would be the detection of gravitational waves. And we have a method to do that, which is called interferometry, and I show it here. So with an interferometer, we start with a laser beam. It comes in from the left, hits a mirror, and we want to see how long it takes for it to go up and back, coming off a mirror on the top, or come to the right and back, hitting a mirror on the right. If there's no gravitational wave and the distances are equal, the light will come back to where it was at the same time. I can invert one with respect to the other, and the light will just cancel, and my little sensor that I have here will stay dark. We'll see nothing. But in fact, if the change is a little bit, then we can see it. The challenge experimentally was that we have to be able to see the difference, if any one of you has ever used an interferometer, to 1 part in 10 to the 12th. Usually when you make an interferometer and you go into, say, freshman or sophomore physics lab, you see little fringes, and you can tell the difference between those fringes to maybe 1 part in 10 or something. We have to do it to 1 part in 10 to the 12th. And that took 20 years or so to be able to develop the tricks and the technologies to be able to do that. The second problem is that here on Earth, the tiny effect that we're trying to measure is terribly small compared to how much the Earth itself is constantly shaking. And so we can't just keep it on the Earth. We have to basically float the detector off the Earth and at the frequencies that we work at. And again, that has to be done to 1 part in 10 to the 12th. So we built 2 big detectors to do that. One of them is in Hanford, Washington, and one of them is in Livingston, Louisiana. And basically, they're 3,000 kilometers apart, and we expect then to see the signals in the 2 to within 10 milliseconds, the time of flight of light going from one to the other. And that's what we tested. These are the detectors themselves. They're each 4 kilometers long. The geography is a little different. In Hanford, Washington, it's high desert. In Livingston, Louisiana, it's pine forest. This is how we can detect them. The area here, if I look on the left, is the size of the signal. 10 to the minus 21, you'll notice, is right here. And this is the frequency that we work at. The shaded area is where we can experimentally see anything without any technical problems. I can't go through the technologies in the talk tonight, but basically we're able to see something down to something like 10 to the minus 22 on the scale that I showed you. Now, what we saw, I showed on the very first slide, is this signal here, and it looked like Einstein's equations. So I just want to say a few other things. That's then the discovery. We've seen more events. You can see this is the second event ever seen, and it has many, many wiggles instead of the first one, which only has 6 or 7 wiggles. Why? Because the 2 black holes that were seen in the second event are much lighter than the ones we saw in the first event. Therefore, being lighter, they can go around faster and basically go to higher frequency in the sensitivity band of our experiment that I showed in the last slide. We've seen a lot of those, and I just show a whole set of them here. If you look at the wiggles, you'll see that they look different from each other. And by studying those now, we're trying to understand astronomy, not just physics, And where do these black holes come from that exist? How do they make themselves? What are their properties and so forth? And as we collect enough of them, we can start to determine some of those features. But after a year or so of detecting gravitational waves, we saw a signal that was quite different. That's shown down in the lower right-hand corner. And instead of it being a few tenths of a second in the apparatus, it went more than a minute. Went for more than a minute in the apparatus. That told us immediately that it was coming not from black holes, but something much, much lighter. We were soon able to identify the fact that what we were seeing wasn't black holes, but another object having a binary system, neutron stars. Neutron stars are a product of an explosion of a star. A star burns up all its fuel, and then gravity wins and it collapses, makes an explosion, which we call a supernova. And the final product is a neutron star. So there are, and we knew that, double neutron stars, and they can go around and merge and collide with each other. Turns out that this observation was that what we saw at the same time from the same object, almost the same time, 1.7 seconds later, they saw some electromagnetic radiation, high energy photons. No other signal has ever been seen from the black holes that we saw. There shouldn't be and hasn't. But from the neutron star, they saw gamma rays 1.7 seconds later. We then alerted the astronomical community around the world where we saw this signal and what its properties were. And astronomers in all different kinds of instruments looked. And so they saw the signal in gamma ray burst and high energy gamma rays. They were able to locate that they see it in the same place in the sky and actually what galaxy it came from. They saw it in the ultraviolet, in the X-ray, and the radio. And all of that, when you put the picture together, can be used to talk about, to be able to calculate what happens physically when two neutron stars collide with each other. And interestingly, that may have solved one of the big problems that physicists have never been able to explain. And that is, how is it that heavy elements got into the earth when the earth was created? How is it that we go into a mine and we're able to find gold or platinum in the mine? Where did it come from? It's very, very difficult to explain because almost the whole universe is made out of hydrogen and helium. Those are just light elements. The heavier elements that we know about generally are thought to come from stars, and even stars when they finally explode. But the whole process of a star burning is nuclear fusion. That's been proven, and that's the process. But nuclear fusion burns first light elements, then heavier and heavier. And eventually, when it gets to iron, it can't go any further. Fusion only works that far. And at that point, it stops having the pressure from the fusion to burn, and gravitational effects then cause it to collapse, and then it becomes a neutron star or something else. In that process, it only makes elements up to maybe iron. So where did we get the heavier ones? Where did we get, for example, our favorite metals, gold and platinum, that we love to put on rings? Where did it come from and how did it get in the earth? People have tried to explain it, because physicists try to explain everything, by having a model for maybe some new effects that might exist in the burning of a star. But they were kind of not very theoretically sound. Now it turns out that the discovery of the collision of two neutron stars is fit to a picture which we call a kilonova. And in that picture, the two neutron stars, when they come together, make heavy elements by something called the R process. And if you do the calculation for the one event that we saw, in that one one collision of two neutron stars that we saw, it made a lot of gold, for example, 100 Earth masses of gold, just in that one collision. Now, of course, that didn't get gold into the Earth, but a neutron collision that happened many years ago made gold at the time the Earth was forming and got into the Earth. So we probably have explained, we think. It's hard to be definitive because we've only seen one example of the neutron stars, but it's quite likely now that this is the best explanation we have for how heavy elements got into the Earth. Let me just end by saying this is all opening up to become a much better science. What's shown here is the very first events we had in 2017, just a few, in 2018 and 2019, and they'll keep going up. We presently are seeing, until the pandemic came, about one new event a week. We're now studying those in detail and seeing all kinds of effects that are new that I don't have time to talk about tonight, but will be in future talks, and this whole new science is opening up. Not only that, we know how to make instruments that would be much more sensitive. And so in the coming decades, gravitational waves, just like astronomy will become more and more accessible through new instruments that are being made. Some of the things that could make it much, much better are illustrated in the picture here. This is a design for a European future detector. One, you can make them bigger, 10-kilometer arms. You can make it a triangle instead of an L like ours is. And that has many advantages, which I don't have time to talk about. You can make it cold. That's a huge difference. In other words, lower it to lower temperature, and then it's actually quieter than the detectors that we have. It's a technical problem to do that, and we haven't done it yet. And you can make the optics fancier so that it picks the frequencies you want to detect gravitational waves instead of all frequencies at once. So the future is really bright, and that's on the Earth's surface. We also are expecting to fly in about 10 years, the first gravitational wave experiment in space called LISA, and that is accessible to different frequencies. So just like in electromagnetic waves, we look at the visible, we look at the infrared, the ultraviolet, and it's a combination of all that that enables you to do such sophisticated astronomy. With gravitational waves, we can do the same. We can make objects and detectors in space, on the Earth, a third kind, which is using pulsar timing, that will give us a broad frequency range. So the future of gravitational waves, I predict, will be similar to what happened in electromagnetic waves. We started 400 years ago when Galileo looked through the first telescope at Jupiter, and he saw 4 moons of Jupiter. There's more than 4, but he saw 4 moons of Jupiter. And that was the birth of modern astronomy, because the first discoveries that were made with something other than the naked eye. Before that, of course, astronomy was the naked eye. In 400 years, we've made all kinds of instruments. Astronomy is tremendously sophisticated. The same can be true of gravitational waves as a kind of astronomy, using gravitational effects instead of electromagnetic effects. And I predict, although I won't be here, that 400 years from now, like we've had in astronomy, that gravitational waves will make the same kind of impact on what we understand about the universe. Thank you.
Thank you very much, sir, for that really insightful lecture. So could you please stop presenting from your end so that we can proceed with a few questions from the audience?
Okay. So how do I get the questions?
So if you could just stop sharing the screen, we would proceed.
Okay, I'll stop sharing. Okay.
Question by Rishabh Srivastava. So, could you please tell if the current laws of physics allow time travel? And if the answer is yes, where do we lag behind in engineering?
By time travel, first, one thing that we can't explain very well, but there's no contradiction to it, is that time always travels in the same direction. That's a very phenomenological question. So we don't have a law except the fact that it's observed that way, that time never goes backwards, it always goes forward. So by time travel, we could travel fast enough so that we end up at a different place because of time dilation in general relativity, and that doesn't break any laws. What we can't do is go backwards in time. So we can't decide to go back to when we were born and see our parents or something. That's doesn't happen as far as we know. As I said, I say that with one caveat, and that is that we don't have any fundamental reason why that's true, but it seems to be what we call causality. It seems to be true that time travels in one direction. We can make it virtually go back a little bit by going faster, going too fast, and so forth, but it isn't the same as going backwards in time.
Thank you, sir. We have another question by Dhruv Patel. So India is the only country apart from US where we are setting up a LIGO in the next few years. So what were the factors that influenced the choice of India as a location for setting up LIGO?
Okay. So for doing most of what I talked about today was general relativity. For that, you don't need other detectors. But what's important, what's become important that I didn't talk about a lot today, a little bit on the neutron star actually, is that correlating a signal that we see gravitationally with electromagnetic observations is very powerful. Because if we look at something, it'll give electromagnetic signals of some sort and gravitational wave signals. And to correlate those, we have to know where the signal came from. So we have to tell where the gravitational wave came from in the sky. The present locations of the gravitational wave detectors aren't very good at doing that. We need to be able to cover the globe better, and especially the southern hemisphere, or nearer the southern hemisphere. So the detector in India helps us give both global coverage and better coverage in the southern hemisphere, and good enough accuracy so that we can tell telescopes where to look. That, just to give a number, is something like tens, not hundreds, but tens of square degrees. If you're that accurate, then telescopes are willing to go look for something. If it's bigger than that, it's hard for telescopes to really cover it. So in order to do that, we need the detector in India. When the detector in India is operational, which should be about 2026, it should be the best detector in the world. The reason it'll be the best detector in the world is that we can put in all the features that we want to put in the detectors without having to waste time, because the other detectors are busy looking for gravitational waves. So we can't put in all the improvements while we're looking for gravitational waves. Well, we can put in all the improvements in the one that'll be in India. So the detector in India, I expect, will be the best detector in the world when it turns on.
There's another question by Barish. So what is the reason for choosing the gravitational detector to be in the shape of a triangle?
The triangle has the advantage that you can see immediately that I could send beams in both directions. So I can go clockwise or counterclockwise. With the L shape, I can't do that. I just send a beam out and it comes back. By having it both clockwise and counterclockwise, I can look for differences between what happens clockwise and counterclockwise. And that gives me an extra, very sensitive way to detect effects that you could never detect in a L-shaped. So it's more powerful in that way. It also basically duplicates the detections. Each corner of the triangle is like the L that we had. So we can take individually those corners and ask 3 times whether we get the same answer. So in experiments that are very difficult, that gets rid of experimental problems. So we have 2 good reasons. One is comparing clockwise and counterclockwise. The second is you basically have 3 instruments that were L's inside the triangle. Thank you. That was a really good question.
Thank you, sir. Thank you for the insights. So there's another question by Prahlad Watson. So why is there a disconnect between the engineering and theoretical sciences when it comes to implementation of concepts, especially with regards to harnessing gravitational waves for usage?
I don't know why it was inferred there's a disconnect, but the challenges technically that are needed to do gravitational waves because the precision is so high were say beyond the state of the art for normal engineering. So in order to push the engineering to be able to do the detectors that we have at the level that we're doing it, we work with very good engineers. It requires teaming scientists with engineers together in order to do that. So let me give a couple examples. The laser that we use, we want it to be a laser that's built by engineers, that is very stable, that will work well. It's like what you buy on a shelf. We don't want to have some laser built by physicists that won't work and it breaks all the time and so forth. But the performance that we require out of the laser is the best laser in the whole world for what we do by far. So we have to develop a very, very special laser. We did that by having a combination of the most advanced group that is developing this kind of laser in the world. It turns out there are 3 different places that were kind of competing with each other and working with industry. One in Palo Alto, California, one in Hanover, Germany, and a third one in Adelaide, Australia. Those are the 3 best places. What we did for LIGO was get those 3 to work together and together on the engineering to decide how to build the best possible laser. That's just one example. But basically what we've done, we could never do it without the engineers. But what we have to do is push the technology beyond what the engineers have already done in a responsible way. And so LIGO is a very close partnership between engineering and physicists. I hope that answers the question.
Yes. So before we come to an end of the lecture, what is the message that you would like to give to the young minds of the globe who are setting out and pursuing a career in the field of pure sciences?
My suggestion to young people is just a couple things. One is you should do science if 2 things are true, I think, at least. One is that it's fun. You shouldn't pick up what you do in life because somebody says that that's interesting or what you should do. If you do science well, I think it is just incredibly enjoyable and fun. And it isn't just making a great discovery. It took us 20 years to make the LIGO discovery. We may have never done it, but it was tremendously challenging and fun all the way. So for me, each day I was having a good time and enjoying myself. Somehow that's important. That's the way we live. So doing something that you have fun with is one thing, and that's important. In terms of science itself, I don't care whether it's chemistry or or physics or biology, gravitational waves or condensed matter physics. I think the reason that you should do it, or the second reason that you should do it, and maybe the most important, is curiosity. If you have in your mind, you're the kind of person, and as a kid, who asks a lot of questions, that you didn't just accept how a microwave works, but want to wonder why it works, how a television works. You wonder how it works. How does this cell phone that we carry around tell us where we are? If those are the kinds of questions that you kind of ask and go on in your mind, then you have the mind of a scientist. So to me, you have to have the mind of a scientist, the curiosity of why we live in this world. Why does an airplane fly? There's just question after question after question that many and most people just take for granted. They never think about it. A scientist wonders, why does an airplane fly? How is it that I put my food in a microwave oven and it cooks it? What, it doesn't have heat? What's going on? And so forth. So if you're driven by curiosity and to do things, you get a satisfaction and it's fun, then you have the combination that means this is probably a good thing for you to do.
That was truly inspirational, sir. So that brings us to the end of today's lecture. Thank you very much, sir, for spending your valuable time with us and for providing us with some key insights on the topic.
Thank you for hosting it, and thank you, my audience, for being patient and being here tonight. I enjoyed it. Thank you.
Thank you very much. To our audience, please find the attendance and feedback form on the chat. Kindly do fill in the same. Participants who attend 4 or more live lectures as a part of Shaastra Spotlight 2021 will get e-certificates. Next up on Shaastra Spotlight Day 3, we have Fireside Chat with Dr. Soumya Swaminathan, Chief Scientist, WHO at 2 p.m., and another lecture by Nobel Laureate Dr. Joachim Frank at 5 p.m. We request you to attend these lectures as well. We thank the audience for tuning in and hope you had a wonderful time. Thank you once again.